Welcome back and welcome to section 2, generic functions and classes. Welcome to video 1, introduction to generic functions and classes. As the title suggests, in this video we're going to take a look at some generic functions, generic classes, and where we use them. So remember from the previous video section that we can supply type information to Java collections. So for example, we can tell Java that we want to create a list of cars, just like this. We say list car in the angled brackets, my car list equals new array list, and that tells the Java compiler that that list or that collection will only ever contain cars. So where car is a class obviously that we have already defined within the scope of our applications. And the list is the Java collections list interface. That's this bit on the left hand side. An array list is a implementation of it, and it happens to be the implementation that's included with the Java programming language. And recall that this allows the compiler to enforce that only cars go in that list, and therefore only cars can come out of that list. And we can also do the same thing, as it happens, with certain function types and classes. So it's not only collections that can be made generic, we can actually make generic functions as well as generic classes of our own. So let's take a look at the basics of generic types. When you define a generic class or declare a variable of a generic class, you use the angle brackets to specify formal type parameters. So the relationship between formal and actual type parameters is similar to the relationship between formal and actual method parameters, except that the type parameters represent type and not the values themselves. Now, type parameters in a generic class can be used almost anywhere a class name can be used. So think about the map interface, for example. It allows us to specify two types when we instantiate it. So it's those type parameters we're talking about, and we reference those type parameters in the definition for our class or our interface, or in fact our functions as well. So if we look at the map interface, extreme simplification of it, it's defined like this. Public interface map, and then the angle brackets k and v. And we can see that the k and the v, in this case the key and the value, actually represent the type of that key and that value. So in this example, the interface is parameterized by two types, k and v. And k and v are used in the interface as concrete types themselves. So we're saying when we put when we put an entry into the map, the key is going to be of type k, which is specified when we instantiate the map, and the value is going to be of type v, which is also specified when we instantiate the map. And likewise, when we want to get the value for a given key, the parameter for get is going to be the type of the key, and the return type is going to be the type of the value that we specify. So you can see here that we're creating a generic interface or generic functionality which can be instantiated in a concrete fashion by handing over specific type parameters that we want to use. So methods that without generics return a type of object now use k or v in their signatures instead, indicating an additional typing constraint. So this allows the compiler to know what's going to happen when we call put and when we call get, and therefore it allows the compiler to enforce the correct type behavior. And as we know, when we instantiate map, we must specify the values for the two type parameters. Now, it just so happens that we can actually write methods in exactly the same way. So generic methods are those that are written with a single method declaration, but can be called with arguments or different types. The compiler will ensure the correctness of whichever type is used. In exactly the same way that we've defined a generic class, we can define a generic method. And generic methods have type parameters before the return type of the method declaration, exactly the same as a class. And type parameters can actually also be bounded, so you don't have to specific type. You can say extends a number, for example. So generic methods can also have different type parameters separated by commas in the method signature. So let's take a look at the syntax for one of those. So for example, let's imagine we wanted to create a generic method that converted an array of something to a list of something else. So we specify the type parameter at the beginning, t. So we're going to return a list of t from an array of t. So imagine we had an array of strings and we wanted to convert it to a list of strings. When we call this, T would be a string. So list of string would be the return type, and the parameter type A would be a string array. And all this does is streams that array and collects it as a list. So in this example, the T in the method signature implies the method will be dealing with a generic type T. And in this example, T is the type of the array that is passed into the function as an argument, as well as the type of the list that gets returned. So T is essentially used twice, both as the parameter argument and as the return type. So for example, if we call this function and we want to do something with a list of integers, we call it like so. List of integers int list equals this dot from array to list with an integer array. And generic methods, as generic classes, can also deal with more than one generic type. So all method types must be added to the method signature. Imagine, for example, that we want to map from one type to another. So we need to supply both the type of the argument as well as the return type, which of course are different because we're converting from one type to another. And we might also want to pass in our own mapper function, for example. So here we're specifying two generic types, T and G. So we're saying our parameter type is going to be T and our return type is going to be G. So we're passing in an array of type T, and we want to go from an array of type T to a list of type G, and we're actually also passing in our own function mapper. So that function mapper will get executed for each entry in our array. So the code for this is quite simple. We're taking a stream from the array, so that's, remember, an array of type T, and then for each entry in that array we're calling the mapper function and then collecting it and returning a list which will be of type G. Now there are a few conventions when it comes to naming type parameters. The recommended naming convention is to use an uppercase single letter name for a type parameter. So we've seen examples with T and G and K and V. It's commonplace to use an uppercase single letter as that type parameter, not to use anything longer than that. And this is a bit different to the C++ convention, and it reflects the assumption that most generic classes and functions will have a very small number of type parameters. Now, it's very unusual to see more than 2 or 3 for any given generic function or class. And there are a couple of common ones. So typically K will be a key, such as the key in a map. V will be a value, such as the contents of a list, a set, or of course the values in a map. E will be if there's some kind of generic exception class, and T will be just any other generic type. Now, one of the really cool features of generics is we can actually create bounded types. So in the previous slides, the type parameters have all been unconstrained or unbounded. That is, it could be anything you like. So T could be a car, a string, an integer, a double, database connection. It could be absolutely anything. Now sometimes we actually need to specify additional constraints on a type parameter. For example, if we could only handle numbers, a number type in our function, it doesn't matter if it's a double, an integer, a float, etc., but our function doesn't know how to deal with strings, we might want to use a bounded type. So we might want to constrain it to be a numeric type parameter. And this means restricting it essentially to a set of types that's accepted by our method or our class. So, for example, we can specify that a method accepts a type and all its subclasses. So number would be an example. In the absence of this type bound, the type is assumed to be bounded by object, which is everything. As we know in Java, everything ultimately extends from object or inherits from object, so that would be unbounded. So let's take that example a little bit further. Let's say we wanted to go from array to list, but we can only do it for numbers. So we would say T, our type parameter, must extend number. So if T was a string, this wouldn't compile. So T has to extend number, and we're going to return a list of T, which we know will be a number, from an array of type T, which we know will also be an array of numbers. So the keyword extends is used here to mean the type T has to extend the upper bound in case of a class. And a type can also have multiple upper bounds. So for example, T must extend number as well as comparable. And the type parameter here is said to be bounded by number and comparator. So that's just a little bit more advanced functionality if you want to use that. It's quite uncommon to see it in practice. Another thing we can do is something called type erasure. Now, generics was added to Java to ensure type safety. So to ensure that generics don't cause an overhead at runtime, the compiler applies a process called type erasure on generics at compile time. So essentially the compiler is trying to do as much of the work of this as possible at compile time, so there's not additional work for the JVM to do at runtime to ensure that these bounds are met. So type erasure will actually remove all types and parameters and replace them with their bounds, or with an object if the type parameter is unbounded. So thus, after the bytecode after compilation will only contain normal classes, interfaces, and methods, not the type parameters themselves. So, for example, this might be our code: public T, list of T from array to list. After type erasure, object T is replaced with object as follows. So T gets swapped out for object. So this is what would be in the bytecode. This is what would be in our code, and that's purely to speed up execution time.